In this video, we'll discuss hypothesis testing, a part of statistical inference which allows us to make statements about broader population characteristics from our samples. The goal of the tools of statistical inference relate to using data from our samples to make statements about the broader population of interest. We may see slopes, means, changes in means, or causal effects in our sample, suggesting a real difference between groups. But do those changes and effects accurately represent what is happening in the broader population? We've actually seen that we can answer these types of questions with confidence intervals. Let's first review the ideas there to set the scene for hypothesis testing. Whether our confidence intervals come from bootstrapping or the central limit theorem, they capture spread in the sampling distribution of our quantity of interest. So they represent a range of likely estimates from other samples and thus a range of plausible guesses for the true population value. We could use these intervals to determine if we had evidence for real, meaningful effects in the broader population. For example, we could run an experiment to see how loud distractions affect reaction times in a sample of college students. The treatment group, experiencing loud distractions, had on average 0.7-second slower reaction times than the control group, who experienced no distractions. The bootstrapping and central limit theorem confidence intervals were both essentially 0.3 to 1.1 seconds. If our criteria for defining a meaningful effect were any non-zero difference between the groups, then we would have evidence for a real meaningful effect in the broader population of adults, because 0 is not contained in this interval. In other words, 0, representing no effect, was not among the reasonable guesses for the truth. However, if our criteria for defining a meaningful effect were at least a 1-second difference between the groups, then we would not have evidence for a meaningful effect in the broader population because 1 is contained in the interval. This means that plausible guesses for the truth include differences that are less than 1. So, if confidence intervals allow us to make statements about broader population effects, why do we need hypothesis testing as a new tool? We'll see that the theory of hypothesis testing allows us to control the probability of making certain errors when we're trying to decide between competing scientific hypotheses. The overarching premise behind hypothesis testing is the following: what would data tend to look like if the comparison or effect of interest were null? That is, if the causal effect of a variable were 0, if the change of interest were 0. To phrase this by using our recent ideas, what would the sampling distribution of our quantity of interest look like if the effect were null? If we know what it looks like, we can try to quantify how odd or unusual is our sample's estimate if the effect is truly null. If our estimate were rather typical, then maybe the true effect really is null. If our estimate were rather unusual, then maybe the true effect really is not null. The first step in carrying out a hypothesis test is to specify the competing hypotheses. These are called the null and alternative hypotheses. These hypotheses are statements about the true population values. The null is a hypothesis of no effect in the broader population and is represented as H0 or more commonly H0. The alternative is a hypothesis of an effect being present and is represented as HA. In the context of our regression models, we make statements about the true population values of the coefficients of interest. The null hypothesis says that beta is equal to 0. This is the hypothesis of no effect because regression coefficients, aside from the intercept, describe changes and effects. The alternative hypothesis states the opposite, that beta is not equal to 0. 0 is called the null value because it is the value that the true population value would take if the null hypothesis were true. Although 0 is the default, we can change this null value to any meaningful value of interest. We always start by assuming that the null hypothesis is true. The idea of innocent until proven guilty applies here. Just like the burden of evidence falls on the prosecution to substantiate guilt, the burden of evidence in a statistical analysis falls on substantiating the alternative hypothesis. We can use our sample to see if our data are compatible or discrepant with the null hypothesis. We do this by computing what is called a test statistic. A test statistic is computed from our data and is the coefficient estimate minus the null value over the standard error of the estimate. So the numerator describes how far our estimate is from the null value, which is a way of measuring discrepancy with the null hypothesis. But we also calibrate this distance by seeing how far this is in terms of standard errors. If we had an estimate that is 1,000 away from the null value, that might seem like a lot. But if the standard error is also 1,000, this is really not so far. In a different sample, that distance could likely have been much smaller. So we can interpret the test statistic as being the answer to the question, how many standard errors is the estimate from the null value? It serves as a way to measure the discrepancy of our data with the null hypothesis. Because the null value is usually 0, the test statistic simplifies to estimate divided by the standard error of the estimate. So large test statistics indicate large discrepancy with the null hypothesis. But how large is large enough? It turns out that the answer to this question varies from setting to setting. That is, test statistic thresholds will vary from situation to situation. This is why it's desirable to have a null hypothesis discrepancy measure that is calibrated across different settings. A quantity called the p-value is a calibrated discrepancy measure. The p-value is the probability of observing a test statistic as extreme as the one from our sample, or even more extreme if the null hypothesis were true. To obtain this probability, we need to look at the sampling distribution of the test statistic. That is, how do the test statistics vary from sample to sample? By the central limit theorem, it ends up being the case that sampling distributions for test statistics tend to follow a normal distribution. This is the case for logistic regression, and for linear regression, test statistics follow a very closely related distribution called the t-distribution. The t-distribution is very close to the normal distribution when the sample size is at least 20 to 30, which is the case in most situations. So if the null hypothesis is true, which is also described as being under the null hypothesis, then the sampling distribution for test statistics will be centered at the null value, 0 in most cases. Suppose that our test statistic were 3. Our coefficient estimate is 3 standard errors away from the null value of 0. This seems fairly discrepant with a null, but let's quantify that more precisely. 3 looks like a fairly extreme value of the test statistic, if indeed the null were true, because it is not near the middle of the distribution. It is not a typical test statistics that samples would generate if indeed the true effect were 0. We can quantify this by looking at the area beyond 3, to the right of 3. It's quite small. This is the idea behind a p-value. The area to the right of 3 is one way of quantifying as or more extreme than our observed test statistic of 3. This area, which happens to be about 0.0015, is the p-value, and in particular, it is called a one-sided p-value because it looks at extreme only on one side. It is the probability of seeing test statistics 3 or higher if the null hypothesis were indeed true. In other words, 0.15% of samples would be expected to produce test statistics, aka discrepancy measures of 3 or higher, if the null were true. That's rare. So note that when one-sided p-values are used, the alternative hypothesis is a little bit different. Because we are looking at positive deviations from the null value, The alternative hypothesis is that the true population value of the coefficient is greater than 0, rather than simply not equal to 0. We use one-sided p-values when we are absolutely sure of the sign of the coefficient. If we're willing to consider that our estimate, and thus our test statistic too, could have been of the opposite sign, then we also need to consider how extreme a test statistic of -3 would have been. The combined area below -3 and above 3 is called the two-sided p-value, and it represents the probability of observing test statistics that are 3 or higher in magnitude, if indeed the null were true. This p-value is 0.003, which means that 0.3% of samples would generate test statistics 3 or higher in magnitude. Like the one-sided p-value, the two-sided p-value is still quite small, meaning that our null hypothesis discrepancy measure, our test statistic, is quite unlikely if indeed the null hypothesis were true. In most situations, the two-sided p-value is the most appropriate because we are not absolutely sure of the sign of the coefficient. But once we have that p-value, we look to see if the p-value is small or large. If the p-value is small, this means that our test statistic, again, our null hypothesis discrepancy measure, this means that our test statistic is large, indicating large discrepancy with the null. If the p-value is large, this means that our test statistic is small and our data are compatible with the null hypothesis. Well, how small is small enough? If the p-value is below a predetermined threshold called the significance level, then we deem the p-value small enough and reject the null hypothesis in favor of the alternative. We reject the claim that the true population value for the coefficient is 0 in favor of saying that it is truly non-zero. There truly is an effect in the broader population. The significance level is denoted with the Greek letter alpha and is usually set at 0.05. If the p-value is greater than or equal to the significance level, we fail to reject the null. It's not that we claim no effect. We just don't have enough evidence to say that there truly is a non-zero effect. The idea of using the significance level alpha as a p-value threshold is actually related to the idea of controlling the probability of making incorrect decisions. We'll see next that rejecting the null only when the p-value is below the significance level controls the probability of one type of error in hypothesis testing. So a p-value alone only tells us whether or not the null hypothesis can be rejected. It actually contains no information about the estimate itself or its uncertainty, the standard error. So p-values should never be reported alone. They should always be accompanied by the estimates and standard errors or confidence intervals.